So I would like to thank Professor Svelto for organizing this. Yeah, but I will use this for this exciting. Yes, I'm okay. I have 2 lasers now. For this exciting symposium, really, which brings together both the past and the present, but the exciting future also. So what I want to tell you about the birth of a new laser, there was kind of blue sky research when I started in this area. I worked for 27 years at Bell Labs. I was there working on artificially structured materials with man-made properties, making ultra-thin layers of semiconductors. We envisioned that we could generate a new class of materials and novel devices. My vision then was so-called band engineering, that we could engineer the band gap of semiconductor in kind of arbitrary way. So that's the context. And I benefit from collaboration from the top crystal growers at Bell Labs, such as Al Cho, who invented this wonderful technique of molecular beam epitaxy. It's commercially available now, by which you can make ultra-thin semiconductor layers down to a few atomic layers. And so you can literally do quantum design of novel materials. So you can view basically the quantum cascade laser as the design of a new class of laser materials. So this is the context. And these are the collaborators. It's a huge number of collaborators over many years. These are the most recent one. We have moved decisively into many industrial applications. We are working with a major company, Hamamatsu Photonics here. This is my current the subset of people working on quantum cascade laser. I've started my own company. I want to tell you about it because it's been a fun experience. And so what spectral range do they cover? This is the spectral range of basically laser. You see, we were, in some sense, was a good timing, because when we entered this field, there was only really one very significant laser in the mid-infrared region. The mid-infrared is a wavelength region roughly from 3 micron wavelengths to, let's say, 25, 30 micron. It happens to be also called the molecular fingerprint region, where most of the molecules absorb light. And of course, this is very important laser, incidentally, invented by my boss at Bell Labs, Kumar Patel, who invented the CO2 laser. Very powerful, has a commercial penetration that is quite significant, but it has some limitations also. It's not a compact laser like you would like to have it for the size of a grain of salt, like the one used for communication, and it has limited tunability. So we exploited this relative vacuum of practical laser in this region here. What the quantum cascades have done is 2 features using the same combination of material. This is very significant. Just by varying the layer thickness, you can cover the whole wavelength range from 3 to roughly 25 micron wavelengths. In principle, you can go with the same material to 300 micron for completely practical reason. If you want to cover now from 30 beyond to 300 micron, now it starts to bordering the field of electronics. Then you switch to gallium arsenide alloys with the same principle. You just vary the layer thickness. You can change the wavelengths practically continuously up to 300 micron or actually beyond. So this is a tailorability. The next step is the tunability, because you can design by engineering this material a broad gain spectrum. You can now position a particular mode, a single mode, and through a variety of tuning techniques, you have wide tunability. Wide tunability means up to 30% of the center wavelength. So it's a combination of tailorability. So I think it's no exaggeration to say that this class of lasers have opened up the field of mid-infrared photonics. So this was the first demonstration. I always say this was an integral work. This is just the last paper. We had to understand transport, resonant tunneling, quantum effects. So the whole work was about 10 years long. So in the current system of funding, at least for the US, it would be difficult to do this in a university right now, certainly in the United States. So you see, this is a very interesting interface because you neighbor with electronics and so forth. So the application is actually quite wide, the application space. It varies from atmospheric chemistry. These are some more, I'm going to show you probably one of the most exciting application because of the societal impact of this work. Environment, this is an emerging field of breath analysis. See, whenever you want to detect molecules, okay, with high sensitivity, high selectivity, in real time, and in a non-invasive, these four things, you can most of the time use quantum cascade laser. They are kind of an ideal source. Then there are security type of application, industrial, this is growing, and so forth. And so I just want to give you, the diode laser is based on the recombination of an electron in the conduction band with an actual hole. And this so means the wavelength is controlled by the actual band gap. It also means, incidentally, that one electron-hole pair that recombines can only give rise to one laser photon. You might say this is trivial. Yes, it's trivial, but it is important that the quantum cascade laser can do much better than that. Okay? And so, which means this is a corollary. If I have a blue laser and I want to change to a different wavelength I read, there is no choice. I have to change material. The quantum cascade laser is not what I like to say a slave of the band gap. So we have eliminated the band gap slavery because it's based on a different optical transition. This is an optical transition that occurs within the conduction band of a quantum well. These are quantized level that forms when I make ultra-thin layer of the order of the de Broglie wavelength, then I form energy levels. And what I can do using another quantum mechanical process, tunneling, I can now lace, if I invert the population here across these two states. Now here you understand the tailorability immediately. If I make a deep enough well so that I can put in, I can accommodate many photon energy, then using the same materials, this band gap and this band gap here, and just changing the thickness, I can tailor, in principle, the wavelengths from, let's say, a few micron, 3, 4 micron, up to maybe 300 micron. If I can now cascade them, that's why quantum cascade. So I put another stage. So after going into here, lasing and you can recycle the electron many times, 20, 100 times. I can get maybe 20, 30, 100 laser photon per electron circulate for the structure. Now, you know, the technology significance, this was not lost to me because all the initial work was done by molecular beam epitaxy, but it occurred to me that, you know, it's obvious, but again, it's one of those obvious things you need to understand that technology to be successful, mass technology need a platform. A platform means if you start to changing your design and so forth, in the case of the laser, the wavelengths, you do not have to change the underlying process by which, that's the platform which we stay. So it occurred to us that, you know, most telecom lasers are made not by molecular beam epitaxy, by vapor phase epitaxy techniques, which you can still make ultra-thin layer. So when I moved to Harvard, I decided I'm going to team up with a big company then working on telecom laser, Agilent technologies, to demonstrate that we could make quantum cascade lasers, nice music, using vapor phase epitaxy. So we succeeded, and this has been quite important because now the reason there's been this rush of many companies making quantum cascade laser is you can now use the same equipment, the same techniques used for optoelectronics at telecommunication wavelength using the same material of telecommunication wavelengths, but in a different wavelengths region, which is a mid-IR because you are not using the actual band gap. So this band gap doesn't matter what it is, but it helps that you use materials that are state-of-the-art for another wavelength region. So this, I claim, is one of the key reasons of the growing commercial penetration. This was the initial structures made by Al Shaw by molecular beam epitaxy. This is how a QC laser works. So it is a ridge. Typically, it's a couple of millimeters long. The width depends on the application, but you're talking typically, 10, maybe 15, 20 micron. And so you can see the thinnest layer then. This was designed to emit around 5 micron wavelengths. So if you want to emit a long wavelengths, you would need these two layers thicker. Now, very quickly, this is an exciting thing, how you can quantum mechanically design a device bottom-up. And I don't have time to really go into any detail. The key point is this. This is the active region. This is an injector region. The reason this is tilted, because I have to apply a bias, an electric field, so I can inject my electron. This is an injection laser. So we use a process called resonant tunneling. And to design these wavelengths, what do we do? To design it at one particular wavelength, we have to change, in particular, this well thickness. Also this, but this is most important. We control this photon energy. This is one thing. Next, we need to have population inversion, you see, which means that this has to be this has to empty the state much faster than it fills, population inversion. So this is done by a trick. By using a thinner well, we inject an extra state here, and it's at a distance such that you minimize in energy, it's at a separation in actual energy, which is equal to a so-called optical phonon, which is a particular vibration of a crystal lattice, so that the electron can go extremely fast from here to here in a sub-picosecond scale. So we design the population inversion. We have to block this pass of the electrons. You see, the electrons can go into here, but they don't because we put like an electron mirror. And this electron mirror is a super lattice, so that now electrons can do the right thing. They can go here, jump down, laze, and then go to the next, laze again, and so forth. So I want to tell you, start immediately about all the scientific. This is a review article. The lead author is a world-renowned chemist, Bob Curl. He's one of the 3 chemists with Kroto and Achel Smalley that won the Nobel Prize in Chemistry for the discovery and the characterization of the buckyball, the famous. This, as he told me, for him was a side project. He got him a Nobel Prize, so not bad for a side project. But his main work has actually been in high-resolution spectroscopy of gases and so forth. So early at Bell Labs, people told me, Federico, you want to start to get some real data spectroscopy, collaborate with the best spectroscopy. So we decided to give out our laser to as many people as we could. At some point, I had 30 collaborators around the world. This has been one of the leading ones. We collaborated from 1996 and we've generated together. So he was the lead author in this review. So this is his statement. It's not really mine. He's been the main user. So you see, they've become really the most useful sources of tunable mid-infrared laser radiation. And now I want to show you this with some examples, some concrete examples. Okay? This is the company where we are now. There is about 2-3 companies every year. There are some major companies, such as this is part of Alcatel, the 3.5 lab of Alcatel Thales. There is Hamamatsu. There is a growing number of companies, and I've sort of lost control. Now I want to tell you a bit, before I go into spectroscopy after, about high power. Now this is in an interesting story. Okay, I teamed up with a company that Kumar Patel created. He's the inventor of the CO2 laser. But one day he actually came to me, which I felt very happy, says, Federico, I've decided to manufacture quantum cascade laser, because I cannot get the power out I get from my CO2 laser, but they are more compact, and for many applications, having them very small is actually important. So together with Kumar Patel, we actually made, my team and his, this very high power QCL. You see, they emit about 3 watts of power, continuous wave, at a wavelength of 4.6 micron. The power level has gone now 10 watts of power, okay? Now, very interesting, we also did, after some very interesting science, these high power, when we started to test this, you see all these modes, you get this proliferation of modes. Now, this is kind of remarkable. You get about 500 longitudinal mode. So we actually discussed, these are room temperature, by the way. This is a so-called coherence effect. Okay, we related this to a collaboration with Franz Kärtner, who all the short pulse people know by reputation. He started to do some modeling, and quickly we realized, I suspected this was a Rabi frequency. You know, you have a very large dipole moment in this transition, high electric field, so I calculate this about 1 terahertz. So maybe there is some coherent effect. And this goes back to history of lasing. As I'm sure Professor Svelto knows, in the early 60s, these very famous theorists, among the fathers of laser theory, Risken in particular, Haken, they predicted that if you were able to go to high power, there would be an instability. And this happens when the so-called Rabi frequency exceeds 1 over the relaxation time. If you like, when the population can rotate between levels if you exclude any relaxation process. So can you observe it? Well, if this rotation frequency called the Rabi is greater than this, this will actually modulate. You see, this rotation will modulate the gain spectrum, and you expect to see sidebands. And we did a very detailed study, and it's quite remarkable. This happens because these were technology quality lasers. So above, this is a regular threshold, and above another threshold, you see this RNGH effect. So this is a coherent phenomena at room temperature in a solid state laser. We did a lot of theory on it and so forth. So now I want to tell, this is an actual company of Kumar Patel. This device that we co-developed, it led to an actual devices that now sell. These are used for countermeasure. There is increasing threat to aircraft, not only military aircrafts, but also civilian aircraft, that a heat-seeking missile could hit. It goes towards the engine, because the engine is a black body around 4.6 micron temperature, and this could be shoulder-held missile. It has happened, yes, it has already once. There was a near miss, and there was a second near miss. So the airline companies are also getting more worried about this. So such a laser could blind the detector of a heat-seeking missile. So this is a high-power type of application. I now want to go into spectroscopy. If I want to select a wavelength, what do? I put a grating, right? And I select a single mode, a single wavelength. The grating can be put on the actual laser. That's how telecom lasers are done. They all have a tiny grating on top, which select or actually bury it into the material to select a single mode. Or if you want to do in particular broad tuning, you can have this configuration with an external grating. And so I want to tell you a bit about the development of spectroscopy. This is work we did at the first 10 years at Bell Labs, 94 to when I left for Harvard, where we decided to target specific molecules. See, this is the atmosphere spectrum. It has 2 atmospheric windows, roughly 3 to 5, 8 to 13 micron. So we designed QC lasers that could emit to observe, to look at, to detect by various techniques. I never did spectroscopy myself, I got a PhD in linear spectroscopy. It says, list this to the professional, which are mostly the chemists and the people that do high-resolution spectroscopy. So we made lasers that could detect all these chemicals, relatively simple, in the atmospheric window. Because you're in an atmospheric window, you can get very high sensitivity. Right? So this work showed collaboration with Bob Curl and other well-known spectroscopy that we could detect chemicals down to a part per billion or actually less, in certain cases part per trillion in volume. So there is very interesting science and many applications in chemical sensing. This is one of the most exciting. It's one of my colleagues at Harvard, very distinguished atmospheric chemist, Professor Steve Wofsy. About 5 years ago, he decided to fly quantum cascade laser in an instrument made by this company. You see here you have basically two QCLs. They are thermoelectrically cooled, so you can control the actual temperature. There is a light, there is a multipass cell. Multipass of the order of 70 meters, what does it do? Because I'm trying to detect pass per billion in molecules, what I need to have is a long path to increase the sensitivity. So this is fairly straightforward. So what is really, people in the field are telling me that the chemists, this is revolutionizing atmospheric chemistry because they are the first measurement of the greenhouse gases in the atmosphere with a high density of grid points. To do a model of climate change, which are highly non-linear, you want a reliable grid. So you want to have a high density of data point with high sensitivity, but also high precision, with a tiny standard deviation. So the breakthrough, they were able to measure many chemicals, and I want to show you the most outstanding example. First, how the measurements was done. This is 5 missions over 3 to 4 years. So the craft goes from the troposphere to the troposphere, up and down, from the south towards near the South Pole to near the North Pole, and measures the various chemicals. So there is the air is sucked in here, and the laser bounces back and forth. You actually tune it by temperature. You temperature tune it by a ramp. You move a ramp of current on top of the laser. And look, this is a remarkable precision. Just look at this. The mixing ratio is the concentration. So they were able to measure CO2 with an enormous precision, 30 parts per billion. That's the standard deviation. And also the other chemicals. So why is this important? I'm going to show you a map of their data. This is essentially the path of the aircraft from south to north. These are the white lines. You see, this is the altitude, troposphere to stratosphere, up to 15,000 meters or even higher. And these are the different concentration. And the punchline, as we like to say in the US, is the following. These are the first measurements to provide a high-resolution section of the atmosphere. And the QL spectrometry, because of the particular design of the laser and the capability, are they're filling a really unique role in making this kind of observation possible. Why are they important? Because you learn new information about the location and strength, and moreover, about the ability to make models. And this I want to skip. Actually, I just want to say, I actually do not want to skip. I want to say a key thing is, what is the line width? Now, you know, like it's explained very well in Svelto's book, that the line width of the laser was predicted in the same paper where the laser was invented, which is a Charlottetown's paper, where they calculated the laser line width. The laser line width is inversely proportional to the actual power. Now, when people made semiconductor laser, they were stunned. They did the first measurement, Moradian et al., others. They thought they didn't satisfy the Charlottetown's thing. And there is a physical reasons for why. Basically, that the gain spectrum of a diode laser is not a symmetric line. So because it doesn't have symmetry, you can show actually the noise, the line width is actually, can be much bigger, or at least significantly bigger than Charlottetown's. Because the QC laser, you see, the spectrum looks like a Lorentzian. When we wrote the first paper, we made an easy prediction. This should be satisfying the Charlottetown's formula. It took over 15 years to demonstrate it. These are the beautiful measurements done by the De Natale group, who is a world-class spectroscopy at Lens in Florence, where he was able to actually, they measure the frequency noise spectral density as a function of frequency, and this would have to go into too many details. At low, if you look at low frequency, you see you're dominated by the shot by noise, by 1/f noise and so forth. But then what you do as you go to high frequency, you get rid of this 1/f type noise. You see this plateau. And if you scale the actual temperature, the actual power of the laser, you see that this plateau follows Charlottetown's. So now they are down to a few hundred hertz, which is very significant. And it's a variant, actually, of Charlottetown. They've done beautiful work on locking, on phaser locking to a near-infrared frequency comb. So there's not time to go into this. I want to tell you another dimension in band engineering. These lasers were relatively small tuning. The tuning of these ones in the atmosphere, you know, it was not significant compared to the center wavelengths, okay? But there might be application, if for chemical sensing you would like to have a tunable source. I call this a universal sensor, that without changing the sensor you can detect in principle a large number of molecules. So what you need, broadband tuning. And so first step is to design the so-called gain spectrum, the gain spectrum of the actual laser. So then you have to go back to your quantum wells, you see. And one thing, in the structure you showed before, I have many stages. All the stages were the same. So you can expect, if all the stages are the same, that this device will have a narrow gain spectrum. But if you now want to make it broad, the idea conceptually, qualitatively is simple. I want to put some stages which are certain at one wavelength, another at another wavelength, and so forth. And so this is what we demonstrated in this paper in Nature, where by changing the thickness of the layers, as we move down the structure in groups of stages, we could have quite a broad gain spectrum. We were able, in fact, to laser simultaneously, was demonstration between sort of 5 micron and 8 micron wavelengths. Now, this has gotten more sophisticated. People have now been saying, well, let's go to the next step. Let's make a single stage significantly broadband. So we can keep maybe all the stages the same. That will be not very broadband, but more broadband than the original one. And then if we want to really get ultra broadband, we can have some layers designed like this. So let me tell you what the design is. How can you make a single stage broadband? Remember, I inject my electron in the upper state by this resonant tunneling, and then this has been quantum mechanically designed so that all the optical transition to these sub-levels, this gives you the broadening, have basically comparable matrix element, dipole matrix elements. So you can get inherently broadband. Then if you can combine, let's say, 5 stages designed at this emission wavelengths and another 5 stages and another, I have designed an ultra broadband gain spectrum. And this has been some very nice work done by my collaborator at Bell Labs, who was my postdoc then, Dr. Jérôme Feist, who is now a professor at the ETH in Zurich, who demonstrated this is a well-known technique. It's called littroconfiguration. Technically, you put an anti-reflection coating, you collimate the thing, you rotate the grating, you can select the wavelength. So they were able to tune. This is a huge tuning from 7.5 to 11.5 micron with 1 watts of peak power, single mode. So this is quite an achievement. So, you know, we said, how can we do better? Well, it's hard to compete when you are with this. But there is a bit of a problem here. This is good to do research in the lab and so forth. This uses 2 piezo. You know, a piezo is a mechanical part. One to rotate and another one, because you have mode hopping process, this is a technical detail. So 2 piezos cost quite a lot, so you cannot carry it. If I want to carry my spectrometer in a rugged place, mounted in my car or my pickup truck, move it where there is a lot of things that are vibrating, this is not an adapt. So we thought we want to make now a very broadband spectrometer that is electronically tunable, not mechanically tunable, very robust and compact. So this is our approach. Conceptually, it's incredibly simple. You design your gain spectrum. I told you how. And then what you do is, in different parts of the chip, by lithography, by standard lithographic method, okay, here you have your mask, your lithographic mask, such that here you have a grating of 9 micron. You can change the grating. So now I imprint the gain spectrum directly into the material, so I have different wavelengths here and so forth. And now this laser has a contact, and this I use off-the-shelf microcontroller. We can send pulses in any sequence we want. This, and get a series of wavelengths. We measure the absorption at these wavelengths, then we can slightly tune the temperature, shift this comb, and we can get, if we want, a continuous spectrum. Many times we don't need a continuous spectrum, so this was the original chip that my students made. You see, we were able to make, these are single modes, okay, and the way it was done is by sequentially pulsing one to the next, so we were able to measure the spectral liquids. These are our laser. This is a commercial spectrometer, which is a box like this. It's a Fourier transform infrared spectrometer. So here is it is. The reason that many companies are interested, we think that QCLs can change the nature of the game for certain spectrometers. We want to have a bright spectrometer. Suppose you want to measure proteins in actual water. You are out of your luck if you use a traditional spectrometer, because an infrared spectrometer has a thermal source, which is called globar, which is not bright. So the infrared will be absorbed very fast in actual water, and if you want to detect the purity of water, so one potential big application of this laser is to detect with this spectrometer, measure the purity of water, what's inside there. This is one application. Incidentally, you can appreciate here the technology. If the wavelengths must come all at the same point for many applications, right? Because if you have a chip like this wavelengths comes out here and so forth. So with Lincoln Labs, which is an important laboratory tied to MIT, we are using a combination of grating. We showed that we can have low pointing error, that all the wavelengths can come out, with a milliradiant angle. So this is important. Now we are working on a chip that this is done on chip using waveguides. So we really make into a spectrometer. So this is the company that we started. It's a Harvard spin-off, and the market that we are trying to target is this. Our vision is the following. We want to have a box which is handheld, which contains a broadband spectrometer which we can carry around. And one important application is in the environment. You want to look maybe the chemicals. There's been a chemical accident, a crime scene. Can I get a chemical image over a broad area? How much time do I have? Okay, good. Yes, I'll be done. So this is called standoff detection. The idea is to do multispectral imaging over a broad area. So what do you need to do that? You have a broadband source, tunable, but then you want to do one more thing. You want to have a fairly high power, because if you want to detect these chemicals, you are at a certain distance. You cannot go close, and you have to illuminate a large area. You need to have high power, and of course, as I said, tunability, and I have to have good beam quality. I forgot to say that, good beam quality. So the requirements are out. Can we make a semiconductor laser for spectroscopy, a quantum cascade laser, in particular a broadband source, that it is single mode in frequency, single transverse mode, which is high beam quality and also high power. So here, so the idea is this, this was done at a distance of 1 meter or 2 meters, proof of principle, loop here. You have something on a wall, you want to detect TNT, you know where the signature of TNT are, and you can see in the image with an infrared camera, you can see when it lights up, when you hit it with the correct wavelengths, you know that you have TNT. Of course, the thing you want to know everything there is on there. So there is a lot of also software, when you have to analyze this. So the next generation for us is we have to make then the basic device is a so-called master oscillator power amplifier to make essentially a narrow device. So it gives you, with a grating, it gives you single mode, longitudinal, and because it is narrow, it is also single transverse mode, so TM00, okay? See, if you want to get power out, there is a simple way. You just make this wider, but then it becomes, you lose the beam quality because you can have many transverse mode. So the idea, which is not a new one, we adapted it to QCL. If I now put an amplifier here, and of course I want to put an anti-reflection coating in here, so this stuff does not laze, okay, and I have an adiabatic taper. The fact that it expands gradually, you can maintain single mode, but now go to high power. And we were able to do it. This is recently published work on a look at the spectrum. This is a standard of telecom engineers that all the engineers know here. Single mode means that you have to put it on a log scale and you have to cut at least 20 dB, if not 30 dB. Okay, and so we were able to get 1.5 watt peak power, single longitudinal, single transverse mode. The next challenge is to make an array of these devices. So we actually did this again. The key is the adiabatic expansion, and this is just published, so there is a lot of improvement to do, but it's still significant. You see, we have about 15 lasers here, okay, between this wavelength and this. Single mode peak power between 2.7 watts to 10 watts. That's an improvement of over an order of magnitude. If you don't put the amplifier, you can typically get not more than 100 milliwatts from a device with a natural grating. Side mode suppression ratio of most lasers was more than 20 dB. So this is a good start. And if we looked at the far field, the majority of them looks actually good. Again, there's a lot of improvement to do, but the direction looks pretty well. They are fairly high brightness. The beam quality is good as a start. I would say it's actually very good. We get an M square of 1.7. Very significant brightness. So the summary is that this technology will lead us to do this standoff spectroscopy, which is very important for application. Non-contact. You know, you might have dangerous stuff there. You want to be far away. You want to illuminate a large area. You need high power, but you need to maintain high beam quality and single mode and widely tunable. So that's what our company focuses on and so forth. In the last few minutes, I want to tell you about this is a challenge that came from another leading atmospheric chemist at Harvard, Professor Jim Anderson. He did the key studies that after the discovery of the ozone hole and the understanding led to the Montreal Protocol. You know, it's basically more or less fixed problem, the ozone hole. Now, what he told me is, you see, he's now wants to fly these robotic aircrafts with no pilot, drones, in inaccessible path where pilots, you just don't want to send pilots. So he wants to do things like go very close to the tundra where there is a huge amount of methane that could come out because it's warming, or he wants to send them in the stratosphere to measure the scattering from aerosols. You know, what chemicals get in the aerosols. So he wants to do spectroscopy, you know, standoff miles away. This is what is exciting for us. He posed me this challenge. Miles away, look at backscattering, okay? But he says, Federico, I don't want lenses. I don't have space. Besides, they're too expensive with the mid-infrared. So can you make a collimated device? So we started with the Hamamatsu. This is a commercial device for Hamamatsu. This is a far field. You see, it's widely divergent. So if it's widely divergent, you can't collimate. You have to put a lens. So we thought, basically, how can we make a contact lens for a laser? That's the idea. So the principle is very simple. You can make an optical antenna. You make a sub-wavelength aperture. This strongly diffracts the light. And then the light couples on this metal grating through a so-called surface wave. It's called a plasmon. It's an electromagnetic wave tied to the surface. They were first studied by Sommerfeld in 1905. And so what happens when this surface wave propagates, it gets scattered at each groove. And since this is equal to a wavelength, now you look in the far field, you will see normally that all these scattered waves are in phase. So you have like an antenna, a series of antennae. You get beam narrowing and high peak power. And we showed this here. And this was the beginning, but it wasn't high enough power. So to make it short now, we decided to, if you want to have do it for a high-powered device, we have to taper our device, which we did. And then if this is wide enough, you do not have to worry about diffraction anymore here. You just worry about diffraction vertically. So we put this collimator. This is a you can call this a one-dimensional set of antennas. Each groove scatters light and creates basically a collimated beam, and that's the result. And now they're ready to go. When his drones are going to be ready, we have to do some more work. This will probably fly in the stratosphere. The nice thing is if you take the original laser, 4 watts of power, peak power is around 8 micron. You put the collimator, you basically lost no power, but you've gained in actual divergence. So you basically can start to do this standoff spectroscopy at high distance. You can now have fun, you can pattern these surfaces any way you want, make collimators, make multiple beams. And the last slide, which I don't have time to say anything except there is a challenge here. If you try to go to terahertz with a quantum cascade laser far infrared, the temperature operation is stuck at basically 200 Kelvin. And this is related to the physics. So we had, I think, a significant understanding that now by combining, we can using nonlinear optics, okay, a process like this where we have 2 cascade lasers, 2 high power beams that beat nonlinearly into a medium. You can design a high K2. To make a story short, and this is the end, I know I'm done, 10 seconds. Okay, this now has been pushed to room temperature with about 100 microwatts of power. So one, I believe, now can cover also the range of far infrared using quantum cascade lasers. And where is the future? The future is still quite exciting. I believe these lasers can be made in the future at telecom wavelengths, which could be very significant. We have started to work with a group of Ted Hansch in Munich to develop mode-locked frequency comb, and also with the De Natale group in Florence. And I think there is a lot of room by combining plasmonics and metamaterial to engineer in an arbitrary way the source, the wavefront, not only of quantum cascade laser, but all kinds of solid-state lasers. So I think this is an exciting direction for future research. Thank you for your attention.